Guys, welcome back to my YouTube channel. In this question, we'll be dealing with strength of material N6, which is a previous paper that was written in 2013. Right, and then you must know that it was an old syllabus, but however, when you are answering this question, we'll apply our new syllabus. Right. So yeah, hopefully you understood that. So we have given question 6, read as follow. A hydraulic cylinder with a ram, we have given a ram there, of 150 diameter lifts a load, given a load of 1 meganewton there. The maximum note, they say the maximum allowable safety tensile stress in the cylinder wall is 20 megapascal tensile. So you know what is tensile, you see the tensile, that we know it's a hoop stress. This one is a hoop stress. Tensile is equal to the maximum allowable, that it's a hoop stress. The maximum allowable safety tensile, it's a hoop stress. And the inside diameter of the cylinder, they say the inside diameter of the cylinder is the same as the ram node. Inside diameter is the same as the ram. That means this diameter will be simply equal to what? To inside diameter, because what is the same as the ram, right? That means that it's our inside, and same as the ram. Use Lim's equation and calculate the following. 6.1, the outer diameter of the cylinder, which is 8 marks. Supposed to calculate the outer diameter. Okay, it's fine. You'll be given this guy. You must take a note. Must scratch your stress distribution graph. You know your stress distribution graph. Stress distribution graph. You'll have something like this, something of this nature. Right from here until there, you'll draw your stuff like that. You'll get to 0 there. I've discussed about this, your stress distribution graph. Then there on the top somewhere, must not reach to 0. Remember, that is Mr. Hook stress there. Remember, this is positive, and this represent the Hook stress. Radial stress, radial is negative. Remember, here it's minus, positive. Right. Remember, this vertical line, this will represent diameter 1, or inside diameter, I can say D1. Right, or here I can write this with D. Let me just use small letter D. This is the inside diameter. So as you have seen, they've said the hydraulic cylinder ram is this 150, but here if you read the question, they say again inside diameter of the cylinder is the same as the diameter of the ram, which is here is the diameter of the ram. It's 150, which is 150 is the same as 0.15 meter. We don't know the diameter, the outside diameter there, because we're supposed to calculate the outside diameter here. So okay, we've given a tensile, the maximum tensile, the maximum tensile stress. If you're given maximum tensile stress, we know this is the hoop stress. We've given the hoop stress there, which is 120. So here at that point, there our hoop stress there at this point, it's 120. It's positive 120 megapascal. We have the hoop stress. Then at this point, what we'll have there, check, note that it's an inside. The ram will be equal, let's say, inside diameter. Automatically, if you have a ram, something like this, the inside here will have something like a ram. Is a sort of like piston. This thing is moving upwards. As you can see here, this is a ram. you'll have something like a plunge, like a piston. This will move upwards and downwards, right? So since it's moving inside, this is an inside. We'll focus on this part. This is a that will represent what? Our cylinder, but the inside diameter will be this part, the inside. Then from the outer part till there, it's a outside diameter. From this point outside until outside there, that will be outer diameter. So the inside, obviously, guys, uh this height, we know the ram is moving, is traveling inside the ram, whereby the ram is traveling inside the cylinder. That means we have the load there that we have to be lift, which is that load is 1 megapascal. So we know that the stress node, the stress, because this is acting inside the cylinder, and then the stress is acting inside, right? That is a stress, right? No, that is a load, right? It's acting inside. And then now to calculate the pressure, remember, pressure inside pressure, we know that inside pressure is equals to what? To radial stress. So if you can check, pressure is given by what? It would be force multiplied by what? By area. So that force is 1 times 10 to the power of 6. Remember, then pi d squared, which we know that we've given, which is 0.15 inside diameter, will simply equals to 0.15. We square this, we'll find the inside pressure. Calculating this, find out the inside pressure will be 56,588 megapascal. However, we know that inside pressure, remember, inside pressure, it's equal to what? To the radial pressure in the inside diameter. So if we write it here on this graph, will be negative. So this will be minus because that portion is negative. Here we have 0 portion, we have 0. Here we have minus 56,588 megapascal. So yeah, are we given this value here in the outside diameter? No, we don't know the value there. We don't know also the value there. We know that is 0, but the one of the, we don't know the minimum what? Hook stress. The minimum hook stress we don't know. We're not given. So nevertheless, let us answer our question. This is what we have, guys. Now we know, according to what we have, we'll be working with this diameter first. This diameters, because we have the information that we need. We're starting at this at the first diameter, but you can see we have there, you can say telling the examiner at the diameter, at the diameter, what is wrong with this pen now? At the diameter 0.15 meter, which is there, which is D. So we know that, we've given that, we've calculated that radial stress is equals to negative. Remember, write it as negative 56,588 megapascal. That is what you've calculated there. However, we know that radial stress is equals to what? A minus B over D squared. Our radial we have is there, which is minus 15. Oh, so not 15, minus 56,588 times 10 to the power of 6 is equals to A. We don't know A, we don't know about B, but our diameter is there, 0.15. Don't forget to square, isn't it? So yeah, this is simply equation 1 so far. Remember, we're still here under this time weight. We're still under this time weight. We are done about that portion, about this point. We are done about this one, but we cannot, don't move to the second point if you have not done about this whole point, because we have something that we've given there on the top. On this same diameter, we also have the hoop stress there at the top, as you can see, which is 120. Now we have given the hoop stress. We know that the hook stress is equals to A plus B over D squared over D squared. We have given there, which is 120 times 10 to the power of 6. Remember, it's megapascal. A we don't know, plus B we don't know. The diameter is simply 0.15, isn't it? Then we square these guys. Then nevertheless, we make A the subject. If we can make A 120 times 10 to the power of 6 minus B over 0.15, we square this will be equals to A. We've made A the subject. There we have equation 1. This we can call it equation 2. Then you know substitution method. You can say substitute equation 1, equation 2. Yeah, let's say equation 2 into equation 1. So where is our equation 1? Here it is there, guys. Let me grab that first. So this is our equation 1. Then we can substitute where we see A, we substitute all of these there. So we'll have minus 56,588 times 10 to the power of 6 is equals to A. We substitute that, which is 120 times 10 to the power of 6 minus B over 0.15 squared. Again we have this minus again there, minus B also, as you have seen there, all over 0.15 squared. So this is what we have here. We have negative 56,588 times 10 to the power of 6. We can take this constant to the other side, will be minus 120 times 10 to the power of 6. There would be left with minus B over 0.15 squared minus B over 0.15 squared. Mathematical check, these things are the same, guys. Exactly the same. Is the same as x plus x is equal to what? 2x. As you can see, those things are very similar, guys. If you are given minus x, you'll have what? Minus 2x. So note, those things are similar. Those one I've highlighted. Apply your algebra there. You'll have minus 56,588 times 10. Okay, you can punch this in right. Yeah, we can reduce that. This will be, or let us, okay, let me just leave it like that. Okay, let me punch this. You can reduce this. Punch it in your calculator. You'll have minus 176,588 0 0 0 equals to minus p minus that will be 2 p's, because when you minus that, isn't it, 2 p's all over these things are the same. Actually, these things they're the same. We'll have two of these things. Here we'll have 0 0.15 squared. This is maths. So yeah, we can make b, multiply this side, divide by minus b both sides. You know what you're supposed to do. Then you'll be left with b as, you know what you're supposed to do there, as 1.987 times 10 to the power of 6. So we have b. Now we can find the value of a from here. You can simply take this there. You can find the value of a now. As you can see, we have b. So the value of a will be 120 times 10 to the power of 6 minus 1.987 times 10 to the power of 6. So here, if we punch this, what can we get? A will be equals to what? 31,689 times 10 to the power of 6. Now, yes, guys, so we have these values now, guys. Now we can want the diameter. Remember, we come to this part now. We know our radial there is 0, isn't it? Is 0 megapascal at that point. So you can take that advantage at outer diameter. Now here you can say at the outer diameter, which is d. Now we come radial is equals to a minus b over d, which is d squared. Here is 0 times 10 to the power of 6 there. So you have seen the value of a we have calculated, which is that 1331,689 times 10 to the power of what? 6. Minus the value of b. There is the value of b. As you can see, is negative also. Negative that over d squared, we don't know, is the one that we want. Then mathematically we have 0, isn't it? So we have 31,689 times 10 to the power of 6 minus this minus, and this minus will be plus 1.987 times 10 to the power of 6 d squared. Take this to the other side. Our b is not minus. Why? Yeah, that is not minus, it's positive. Sorry guys, here our b is positive. Sorry about this. Here we have minus 1.987 times 10 to the power of 6 divided by d squared. Then yeah, take this to the other side, will be negative 31 comma 689 times 10 to the power of 6 is equals to negative 1 comma 987 times 10 to the power of 6 over d squared. Then you know what is left is a mere to multiply there. You'll have negative 31,689 times 10 to the power of 6 d squared into minus 1,987 times 10 to the power of 6. Then we divide by this, negative 31,689 times 10 to the power of 6 both sides. Right. This cancel, will have d squared. We take the square root also. Negative and negative will cancel. Simply take the square root, will have 1,98. Right. 98. Here we have 7. 7 times 10 to the power of 6 divided by 31,689 times 10 to the power of 6. Punch this on our calculate. Therefore d will be equals to 0,25 meter. Then if you want this to be in millimeter, you multiply by 1000, then this will be 250 millimeter. So yeah, that is our outside diameter. We have now the outside diameter. So yeah, it's your 8 marks there. Then 6.2 says calculate the longitudinal stress. Longitudinal stress, right? We know that longitudinal stress is given by longitudinal stress is the inside pressure multiplied by inside diameter. We square this into outside diameter squared minus inside diameter squared. So the pressure is what? We have calculated it. Here it is. As you can see there, 56, 5,588, 56, 588 megapascal times 10 to the power of 6. Multiplied by inside diameter, which was 0,15. Then we square. Outside diameter is the one that we got, which is 0,25. Then we square this minus 0,15. Then we square these guys. Then what it will be our answer there? If you pound that, this multiplication will be 31,831. This is in megapascal, right? This is in megapascal. So yeah, then we have the last question. Obviously, the strain, the outer strain at the outer diameter of the cylinder wall, if Young modulus is this 1 max. Okay, strain it out. Okay, the original strain. This is nice. How cool is this? So here is the formula for that strain. We are answering this question. Will be 1 over E Young modulus into Hooke's stress minus Poisson ratio multiplied by radial stress. So 1 over this you have given is 200 times 10 to the power of 9 into Hooke's stress is the one that you've calculated. You've given it's 120 times 10 to the power of 6. You've given it here, Remember 120 minus, you are not given the poise ratio, we are not given, so it's simply 0. Since you are not given, if you are not given, substitute 0. So anything when you multiply by 0, you know this will simply, all this side will be equals to what? To 0. So since you multiply by 0, you will simply have 0. Everything there will be what? Is 0. So yeah, we can do like that. Everything will simply equals to 0. So per se you will have this to be 1, 2, 2 times 10 power of 9 into 1, 0, 0. So this is 1. So yeah, if we punch this, you will get, remember the strain has no SI units either. The strain has no SI units. Oh, the strain has no SI units. So the strain does not have SI units. Is this will be 600 times 10 to the power of minus 6. Or someone can write this in this format: 6 times 10 to the power of minus 4. It's a one and the same thing. One is exactly, just depend on your scientific form. So this is what it is, guys. So thank you for watching, and please do not forget to subscribe to my YouTube channel and click that notification button so that you'll be notified whenever I post a new video. You can comment and you can share this to your fellow classmates. All the best, guys.